Okay, so welcome back to another video. So in today's video we have the integral of 0 to 1 of 1 divided by 1 plus the floor function of 1 over x dx. So floor functions are usually defined as the greatest integer function. So basically for any x, it's the greatest integer that is less than or equal to x. So for example, we have like pi, so 3.14. The floor of pi is equal to 3. 1 over 4, which is 0.25. The floor of 1 over 4 is just 0. Let's say the floor of e, which is 2.71. The floor of e is equal to 2. So basically, these numbers are integers that is less than or equal to any x output you choose. So simply, we have that the floor of 1 over x, it's one thing to consider is that the floor of 1 over x is actually known as a piecewise constant. So let me just write this little note, is that the floor of 1 over x is a piecewise constant. Okay, so and then let's actually define what our output looks like for the function of the floor of 1 over x. So okay, so this is equal to, and consider, and the way we're going to do this is, let's actually start with x equals to 1 and then work our way backwards as we're going to x is equal to 0. And this will come out nice and smooth when we're trying to integrate this integral here. So if we start with 1 over 1, so x is equal to 1, let's say, so it's just 1. But if we were to consider values strictly greater than 1, so 2, let's say, 1 over 2 is, the floor is just 0, 1 over 3, if x is equal 3, it's 0, and so forth. So therefore we can say that the floor of 1 over x is equal to 0 such that x is strictly greater than 1. Okay? So now let's try something strictly less than 1. So let's say 0.75, 3 over 4. So 1 divided by 3 over 4, flip the reciprocal, it's 4 over 3. So the floor of that is 1. Or let's actually try 1/2. So, well, to put it simply, anything. So let me just write 1. But that's considered if it's strictly less than 1/2 or greater than 1/2, strictly greater than 1/2, and then strictly less than 1. Okay. Like I said, we could try 3 over 4. We plug this into here, then we get that its floor is just 1. So let's try something less than half, for example. So maybe 0.25. For example. So, or rather, let's try something maybe like 1 over 3. So 1 over 3, the floor of that is 3. So let's try something greater than 1 over 3. So somewhere between I don't know, let's say 0.4. What is that? 0.4. That's 2 over 5. Okay, so 1 over 2 over 5 is 5 over 2. 2.5, the floor of that is actually 2. So now we can actually use our restriction that it's equal to 2, such that it's 1 over 3 is strictly greater than x, which is strictly less than 1 over half. And then the list goes on so forth. Using with our definition with this piecewise constant, we can use this sketch we have to actually rewrite our integral in terms of sums. So we're actually breaking up our bounds of integrals, in other words. So we write this. So the integral from 0 to 1 of 1 divided by 1 plus the floor of 1 over x dx. This is just equal to, so let's start with 1. So our upper bound being 1 and our lower bound being 2. Okay, so 1 and then 1/2. And then simply we could just replace our floor of 1 over x for 1. So this is just 1 over 1 plus 1 dx, then plus the integral from, now it's from 1/2 to 1 over 3 of 1 over 1 plus 2 dx, and then plus the integral. You're starting to see a pattern. We're going like our denominators is actually decreasing by, or rather increasing by 1. So the integral, we're going smaller and smaller. So 1 over 3, and then 1 over 4 of 1 over 1 plus 3 dx, and then so on and so forth. Okay, so using this, then we can actually conclude that we can actually rewrite our given integral as a in a form of a series, an infinite series in particular. So 1 over the floor, 1 over x dx. This is just equal to the infinite series. So we're starting at n is equal to 1. So n is equal to 1 of the integral of, so this means this is actually, so our bounds would have to be 1 over n, and then the lower bound will be 1 over n plus 1 of 1 divided by 1 plus n dx. Okay, cool. Now notice that 1 over 1 plus n is just a constant, so simply I could just move that outside. So this is n is equal to 1 of 1 over 1 plus n, and the integral from 1 over n to, from 1 over n plus 1 to 1 over n of just dx. Okay, so integrating this is simple. So this is simply just x evaluated at our bounds of 1 over n, and then 1 over n plus 1, which is simply just 1 over n minus 1 over n plus 1. Okay, then I can substitute that back. So that means we have the series is the infinite series of from n is equal to 1. Yes, so this is 1 over n plus 1, and then multiply with our evaluated integrated integral over here. So this is 1 over n, then minus 1 over n plus 1. Now we can just distribute our 1 over n plus 1 into our inside brackets. So rewrite this again. This is just 1 divided by n times n plus 1, then minus 1 divided by n plus 1 square. So now all we have to do is just evaluate our series. So let me actually express this into two series. So this is just a infinite series equals to 1 of 1 over n times n plus 1, and then minus the infinite series of 1 over n plus 1 square. Okay, now now we just have to solve. Now we just have to evaluate these series. So let's actually first evaluate this expression first, or the series rather. So the infinite series from n is equal to 1 to infinity of 1 divided by n times n plus 1. Okay, let's just focus on the denominator, and we can actually split this up into partial fractions. So this is n plus 1. So we have to solve for our coefficients a and b, but that's not really hard to show. I'll just show the full work anyway, just for the sake of it. Then plus b times n equal to 1. Okay, so let's see, if we let a is equal to -1, so this should be negative, or this should be 0, and the -1 here is equals 1. And then over here, if I let n is equal to 0 associated with our coefficient b, so this should be a times 1 plus b times 0 equals 1. So therefore, b is equal to -1, and then a is equal to just 1. Okay, so therefore we have our coefficients, so this is 1 over n plus or minus 1 over n plus 1. Okay, so let me just substitute this back. So this is the series. N is equal to 1 of 1 over n minus 1 over n plus 1. Okay, nice. Now I'm gonna move over here, and now what I want to do is let's actually expand this sum out. So that means, I should write this in red. So when we expand this series out over here, so this means let me just rewrite this series again a second time. So the infinite series, simply we expand this out. If we let n is, so we start with our index n is equal to 1, okay? So this means this is 1 minus 1 over 2, okay? N plus, now n is equal to 2, so this is 1/2 over 1/2 minus 1 over 3, then plus 1 over 3, this is just n is equal to 3, so minus 1 over 4, and so on. So notice that -1/2 plus 1/2 cancels, -1/3 plus 1/3 cancels, so on and so forth. What you're looking at, this is a telescoping series, so the terms cancel out, and so the only thing we're left with is just this constant 1. So therefore, this series n is equal to 1 of 1 over n minus 1 over n plus 1 is equal to 1, or rather I can just rewrite what we have from earlier. So 1 over n, that's supposed to be n times, this is just equal to 1. Okay, nice. So that's our first evaluated term for now. And now we just got to evaluate the second, which is the 1 over n plus 1 square. Okay, I'm actually going to have to go back and write in red just to establish something. So now the next thing is, just like I said, we have to solve this series here, the infinite series of 1 over n plus 1 square. So something we want to recall is Basil's problem. So Basil's problem. So simply, the definition is as follows. So it's the infinite series from n is equal to 1 of 1 divided by n squared. Okay, is simply just well, let me expand the series out before we write the answer to it. So this is just 1 over 1 square plus 1 over 2 square plus 1 over 3 square, and then so on and so forth. Simply, this series actually equals to pi squared divided by 6. Okay, so we have that. Now let's actually using this, let's actually expand this series out and see if we have some correlation with Basil's problem. So that means if we write this, n is equal to 1 of n plus 1 squared. So if I let n is equal to 1, so this is just so this is 2 squared plus 2, so this is 3 square, then plus 1 over 4 square, plus dot dot dot. Okay, so now notice that the terms here share the same terms over here. So to put it simply, let me actually rewrite Basil's problem so that we can actually substitute with our other infinite series. So Basil's problem, rewrite this again. So this is the infinite series of 1 over n squared is equal to 1 right here. And then plus 1 over 2 squared plus 3 squared, or 1 over 2 squared plus 1 over 3 squared, and then so on and so forth, which is exactly the series here. So I'll just replace that with our other infinite series over here. N is equal to 1 of, let's see, yeah, 1 over n plus 1 squared. Okay, so we have that. Now I can just replace this, which is this Basil's problem is just equal to pi squared divided by 6 equals the same thing. 1 and then 1 divided by n plus 1 squared. And then I can just subtract 1. So therefore this series is just equal to pi squared divided by 6 minus 1. Okay, so we have this. So we have that 1 is equal to this series, and then pi squared divided by 6 minus 1 is equal to this series. So now, just to reiterate everything, so rewrite our series again one more time. Is equal to 1, and then 1 divided by n times n plus 1 minus the other series. N is equal to 1 of 1 divided by n plus 1 squared. This is equal to, so it's 1, then minus pi squared divided by 6 minus 1. And we get that this is just equal to 2 minus pi squared divided by 6. Okay, and we are done. So to reiterate, so therefore I can conclude that the integral from 0 to 1 of 1 divided by 1 plus the floor of 1 over x dx is simply just equal to 2 minus pi squared divided by 6. And if you want to simplify this out, this is the same thing as 12 minus pi squared divided by 6. So that's our final answer, like so. Alright, that's pretty neat. Floor integrals are really interesting.